given a diagram and showing the curve of the equation y equals x cubed minus 2x squared all times ln x. And the curve has a point of inflection at the point M. So remember, this is where the curve goes from either concave to convex or convex to concave. In this question, we can see the gradient is decreasing to the left of M, and it starts increasing. So it's actually concave followed by convex. And then, let's get into this. So we're going to need to find dy by dx first of all. So I've got my u and my v. U dash will equal 3x squared minus 4x, and v dash will equal 1 over x. So dy by dx is u dash v plus u v dash. So I'm going to get 3x squared minus 4x ln x plus x cubed minus 2x squared times 1 over x. I can just write it as over x. And that will be 3x squared minus 4x ln x plus x squared minus 2x. Then we've got to differentiate again. Okay, product rule again. I'm actually going to do it a little bit quicker this time. I'm not going to write down the u and v dash and so on, but you can if you want. So I'm just going to go with the u dash, which is going to be 6x minus 4 and times by v. And then add u times by v dash, which again is 1 over x, so I divide by x. Then I'll be adding 2x and minusing 2. And let's just tidy this up. We're going to get 6x minus 4 ln x plus 3x minus 4 plus 2x minus 2. 6x minus 4 ln x plus 5x minus 6. Okay, now we can investigate the point of inflection bit. Now, a point of inflection is actually where the second derivative changes sign. So in general, you can't just set it equal to 0. You have to also show that it changes sign. But in this particular case, we can see it's changing sign because from the graph. I just want to I just, in answers, they just said it equal to 0, but we need to, in general, to show it there is one, show that it also changes sign. Can see dy by dx changes. And it is possible for, the second derivative. It's possible for the second derivative to change sign without ever becoming 0. There are like particular functions that do that, but that's not happening here. It's where it's when the gradient itself wouldn't be defined, and it's defined everywhere here. So I can see d2y by dx squared changes sign. So set equal to 0. I've got to be honest, you'd get away with just setting equal to 0, but I just, from a good maths point of view, we need to reference the fact that it's changing sign. Okay, right, I'm done with that, but it's important. So what I'm going to do now is, just set it equal to 0, and I'm going to try and rearrange. So I'm going to come down here. So therefore, 6x minus 4 ln x plus 5x minus 6 equals 0. And I now want to sort of make x the subject. It's not actually making x the subject because it's on both sides, but I want to get this one as a subject. Okay, x in terms of load of stuff and ln x. So what I can do is say that 5x is equal to 6 minus 6x minus 4 ln x, and therefore x is equal to 6. Now they've changed it round. They've swapped these two around to make it 4 minus 6x, and then they've changed this to a positive. They are the same thing, so we can just go straight there now. 6 plus 4 minus 6x ln x over 5. as required. Use an iterative formula based on the equation in A part 1 to determine the x-coordinate of m correct to 2 decimal places. Use an initial value of 1.1. So you only learn about 2 iterative methods in A-level. One of them is Newton-Raphson, but not using that here. Okay, it doesn't mean to start finding the derivative again. It wants us to use fixed point iteration. It's in the perfect form for it. So let's x n plus 1 equals 6 plus 4 minus 6 xn ln xn over 5. And just a quick recap of how this method works. We've got the line y equals x on the right, and then the function, so on the left, y equals x, and the function on the right, I don't know what it looks like, but here's an example what it might look like. And we want to find where these two lines intersect. And actually that is the same as the solution to the original equation, that one up there. So what we do is we put in a value of x. This is our starting value. And then we go along and that becomes our new value. Okay, and in the process of going along to the right means that I'm setting my x equal to my y, essentially. So that becomes my x2. I then put it in, find my new y value, go along, that becomes my x3, and we just cycle around, and you can see, well, in this particular case, it's a cobweb diagram, it spirals in towards a solution. It's not always guaranteed to, you can guarantee it's going to happen here because they've asked us to solve it, but that is what is happening. So we've got the x0 is equal to 1.1, and then we just got to put in enough values to get it correct to 2 decimal places, but we've got to show the result along the way. Each result. So I don't know how many I'm going to need. I've just written a few down. So we're going to do 1.1 equals to get that as our answer button, and that becomes our xn. Our red one. I'm just going to use the purple one because I'm covering it up, but all my x's are now xn. They're going to be the answer button. So I've got 6 plus 4 minus 6 times the answer, ln times the answer over 5. And we get 1.15. Just write a few more down. So 1.1504. And if you keep pressing equals, you just get more and more. 1.1186, 1.1391. It's still changing to, remember, it's 2 decimal places, 1 to accurate 2, so I've got to keep going. x4 is 1.1261. x5 is 1.134. Now it looks like it's going towards 1.13. So at this point, once you get to that 1.134, let's do another one. Okay, let's just press equals lots of times now, and we can see it's going to be 1.13. So I don't need to write any more out. I think in the mark scheme they did write one more out, but we can say that x is going to be 1.13. And we've got one more part of this question to do. We've got to determine the exact area of the shaded region. So I'll just bring the diagram back. Here it is. Giving our answer in the form p ln q minus r, where p and r are positive rational numbers and q is a positive integer. So we need to first of all work out these points here to see where we're integrating. So I'm going to set this equal to 0. And then I can factorize as much as possible, so I can bring an x squared out, leaving me x minus 2. So then x is equal to 0, 2, or ln x is equal to 0, which means x is equal to e to the 0, which is 1. So I've got 0, 1, and 2. 0, 1, and 2. The area, and be really careful here, because when we integrate, we're actually going to get a negative value. So the area is going to be minus the integral of 2, 1, x cubed minus 2x squared ln x. Now you can either do the integral and then make it negative, but here's something you might want to consider. You can actually just swap the limits around. When you swap the limits around, it just changes it from positive to negative. So actually, I'm just, in basically bringing this minus in. Because remember, when you put the limits in, you do whatever it is, you put 2 in, and then you minus all the stuff when you put 1 in. So you're just going to get the negative when you put 1 in and minus all the stuff with 2 in. That will always work. Okay, if you want to stick with the minus on the outside, no problem. Right, and this is actually a classic integration by parts. You can use the little acronym LATE, which means we're going to use logs. If we've got a log there, that tends to be our u. And then if there's no log, it'll be algebra, then trig, then exponentials. But the key one is if you see a log, make that u. Then this will be v dash. So u dash will be 1 over x, and v will be a quarter x to the 4 minus 2 over 3 x cubed. So then I get uv evaluated between 1 and 2 minus the integral from 2 to 1 of u dash v. So I get a quarter x to the 4 minus 2/3 x to the 3 times ln x. We just tend to write ln x on the right. That's why I've actually swapped it round. Minus u dash v. So actually I just need to divide a quarter x to the 4 minus 2/3 x cubed by x. So a quarter x to the 3 minus 2/3, sorry, not, minus 2/3 x squared. Now I could just start subbing in the values actually, which I think I'm going to do. So I get a quarter minus 2/3 times ln 1. Actually, that is going to become 0. Minus a quarter times 2 to the 4. That's 16 over 4. That's 4. Minus 2/3 times 8. So 16 over 3 ln 2. And then I'm minusing. It's going to be 1 over 16 x to the 4 minus 2 over 9 x to the 3 evaluated between 1 and 2. Let's figure out what 4 minus 16 over 3 is. So minus 4 over 3. So I'm actually going to get 4 over 3 ln 2. Then minus 1 over 16 minus 2 over 9 minus, well, we're going to sub in 2. So it's going to be 1 over 16 times 16. That's going to be 1 minus 16 over 9. Okay, it's just a lot of brackets there to deal with. So I'll use my calculator here. Right, just 1 over 16 minus 2 over 9 minus, now I need a bracket, 1 minus 16 over 9, close bracket, gives us 89 over 144. Actually, that is in the form that we're asked for. Okay, p ln q minus r. That's the thing, if you forgot to make it negative, you might have spotted that point. Okay, you know what? These are not, for you, you wouldn't have got positive numbers for p. But this is absolutely fine. It says q is a positive integer, so this is perfect. That is our answer. Well done.